Okay, students, so we've already talked about general kinematics in terms of distinguishing between distance and displacement and speed and velocity and those vector quantities, and how whether you're talking about scalars and vectors really makes a big difference. We've also talked a lot about acceleration, and we generally always treat acceleration as a vector because whether it's positive or negative relative to the velocity of the object moving determines whether the object is speeding up or slowing down. So I'm going to spend a little bit of time here talking about the concept of instantaneous and average. And it's really important that you understand the difference between the two because it has great implications in terms of how you solve a problem, and especially how you look at motion graphs and graphing kinematics, which is going to come up pretty soon. Okay, so generally for an object that moves distance delta s in a time delta t, when computing the speed, we use v equals delta s over delta t, or change in distance over change in time. Now, when we do this, we're really computing the average speed, since we don't know exactly what's happening at every instant of time between t equals 0 and t equals some later time t, or between the initial distance and the final distance. So we say generally that v average equals delta s over delta t, and we indicate the average by a little subscript. AVE is usually what we do. Now, you could also do v with a little bar over it, but I usually don't do this because it gets a little bit confusing with the bar and the vector, which makes it velocity. So you just want to be really careful about that. Generally, I use the subscript AVE, and that's the average speed over a time period. Again, average speed is the total distance over the total time. Okay. Now, this is very different from the instantaneous speed, which basically tells you how fast at any instant in time the object is going. Okay. So a good example of this is when you're driving home. You know, what shows on your speedometer is not the average speed for your whole trip, although your car will generally compute that. What shows on the speedometer is the instantaneous speed, or the speed at any given instant. And when I say instant, I don't mean that the time interval delta t is 0. That's actually not possible. But what I'm talking about is that delta t is measured over a very, very, very small time. Okay. Now, I'm going to teach you guys a little bit about calculus. You haven't learned about derivatives yet, probably in calculus. Don't get freaked out by it. It's actually quite simple. Whatever you learn and absorb here about derivatives will really help you in your math class when you do start studying derivatives. Okay? Generally, in calculus, we say that the instantaneous speed, when we're talking about instantaneous speed, instead of using uppercase delta, we use lowercase delta. That's this funky looking d right here. And what that lowercase delta means is that these intervals, delta s and delta t, are infinitesimally small, or infinitely small, but they're not 0. Okay, so delta is a finite change in, little delta is an infinitely small change in. Okay, now, the way that we compute the instantaneous speed is we say, okay, well, because little delta t is an infinitesimally small delta t, we say in calculus that little delta s over little delta t equals the limit as delta t approaches 0 of big delta s over big delta t. Okay? So, again, what this means is that delta t, the numerator of this, or sorry, the denominator of this fraction, goes to 0, but it never becomes 0. Clearly, it can't become 0, because if it does, then you would have an infinite quantity here, which doesn't make any sense. Okay. Now, if the distance varies linearly with time, then the two of these are the same, and I'll show you examples of that when we study motion graphs. Okay. Usually, often we deal with situations where the distance does not vary linearly with time, so we got to deal with this, okay? And what this really amounts to graphically is finding the slope of the tangent line to that particular magical point, t, okay? Now, whatever the quantity in physics, whatever we're talking about, unless we specify otherwise, a variable means the instantaneous quantity. If it's the average, it will also be indicated. So therefore, if you see v, if I ask you to find v, or if you're using an equation with v, that is the instantaneous speed. Okay. If it's average, I will always say v average, or sometimes you'll see a bar over the top. Okay. All right. Now, we're going to talk a little bit more about this concept of a limit, this crazy thing as delta t goes to 0. You've probably never seen that before, so let me just spend one slide here just explaining it. It's very important. Again, this is mathematics. This is calculus. but if you follow along with me, you'll be ahead of the game in terms of this topic when you study it in math. And remember that Newton and Leibniz invented calculus concurrently. Newton invented calculus specifically to solve physics problems because he was dealing with exactly the kinds of graphs you'll be dealing with in kinematics, okay? So it's really important to have a grasp of it, all right? Okay, so you have this graph, this light blue curve is a graph of distance against time, okay? Distance in meters and time in seconds, okay? Now, if I wish to find the instantaneous speed at a particular point t below, which is this point right here, okay? I want to find the instantaneous speed, okay? So v of t, okay, which is a function of t. The speed is a function of t, which itself is a slope function, okay? It's the slope of the tangent line at t, all right? And we call this in math, we call this the derivative of s of t at t, okay? Now, there's only one line that gives v of t, and that's the brown one, okay? Remember, we're asked to find the speed at this exact time t right here. There's only one tangent line shown here, and that's the brown one that gives that. The other three are not tangent lines, they're secant lines because they intersect the curve in 2 points, okay? The brown line only intersects the curve in 1 point, which is the point that we are interested in, okay? So the way that I would compute this is I'd say, okay, I'm going to talk about 3 different points at 1, 2, and 3, 3 different lines, 1, 2, and 3. I'm going to start with 1, and you'll see that as we get closer and closer to the brown tangent line, okay, basically the secant lines get closer and closer to actually being that tangent line. And what it amounts to is this interval between t and t prime, t double prime, and t triple prime getting smaller and smaller, approaching 0. I'll show you what I mean. So for example, if I want to compute the average or the gradient of line 1, okay, I'm calling that v triple prime average because t triple prime is the time out here, indicated by three primes. It's the change in distance over the change in time. Well, this is the rise over the run. This is going to be s of t triple prime minus s of t all over t triple prime minus t. Okay. For line 2, same thing, except for I have s t double prime and t double prime. And for line 3, which is the one that has the minimum slope just above the brown tangent line, which is what we're interested in finding, it's st of prime minus s of t all over t prime minus t. Okay, so you can see that as we get closer, as this point gets closer to t, the slope of the secant line ends up coming down and approaching the tangent line. It doesn't become a tangent line until it actually becomes the brown line, okay, which is the slope at t, which is what we're asked to find, okay? Now, again, as the interval along the t-axis gets smaller, the purple secant lines approach the brown tangent line. As this interval approaches 0, it actually becomes the tangent line at t. So that's what I mean when I say as delta t approaches 0. Delta t is the difference between t and these other values of t, okay? Here's my first delta t, t triple prime minus t. Here's my second delta t, t double prime minus t. And here's my third delta t, which is t prime minus t. You can see that that interval is getting smaller and smaller, approaching 0, okay? So, again, that's what I mean when I say that little delta s over little delta t is the limit of big delta t goes to 0. That's how we say it. Okay, we say it's the limit of delta s over delta t as delta t goes to 0. That is the instantaneous velocity at t. And isn't it cool that Newton invented all of this in order to solve this problem? Because he realized that he had this big problem finding the instantaneous velocity, and this is how he solved it. And it basically gave rise to a whole new branch of mathematics called calculus. So really impressive. Okay, remember, delta t goes to 0, but it never becomes 0, because if it becomes 0, this whole expression blows up as infinity. So it doesn't make any sense that way. Okay? All right. Okay, so here's an example. Go ahead and pause the video and try this example on your own. Okay, so I have the following distance time graph. S is a function of t. It's a concave up curve. I have the average between 0 and 2. Well, that's just the slope of the green line, which is 1 meter per second. The average between 2 and 4 is the slope of this red line, as I have drawn here, 3 meters per second. The instantaneous v at 2 seconds is the slope of the purple tangent line, which I got is 2 meters per second. Again, there's a range of what I would accept. Somewhere around 2 would be fine. It depends on how you actually draw your tangent line. The instantaneous speed at 3.5, again, the slope of the black line, which I got around 3.8. There's a range. And the average between 0 and 4 is simply the slope of this blue line, which I have about 2 meters per second. Okay? Okay, so I'm going to talk about something else really important. We're going to get away from calculus for just a minute. It will come back. You'll see it a lot again. We're going to talk about fluid resistance and terminal velocity. It's a very important topic in the IB. Okay. Now, you know from your studies of physics before that near the surface of the Earth, if I drop something, it accelerates at a rate of 9.8 meters per second every second downwards towards the center of the Earth. Okay, we studied this last year. The negative sign here means that the acceleration, which we treat as a vector, g is an acceleration vector, but it's such an important acceleration that it gets its own variable name, which is little g. It's negative because it's always pointing downwards towards the center of the Earth, and we generally consider downwards to be negative and positive to be upwards. Okay, all right. It actually varies around different places around the surface of the Earth. Okay, it depends on a couple of things. It depends on how far away you are from the center of the Earth. So places at a higher elevation have a slightly lower acceleration due to gravity. But it also has to do with the makeup of the Earth that's between a particular point on the surface and the center of the Earth, like the density of the rock, whether you're near an ocean, the density of this and that makes a difference. But generally what we do is we treat it as negative 9.81 meters per second squared anywhere on the surface of the Earth. That's just an average that we tend to use. In the IB, when you're solving paper 2 questions, or certainly paper 1 questions, you're free to use negative 10 meters per second squared if you want to. Okay. Now, from Newton's second law, which is F equals ma, you know that W equals mg. We derived this last year where we came up with an expression for the weight of an object being the mass of the object times the acceleration due to gravity. Now, obviously, an object does not need to be accelerating or moving in order to have force, in order to have a weight acting upon it. Everything has a weight vector. It has a force acting on it when it's near the surface of the Earth, and that's given exactly by W equals mg. Okay? All right? So, for example, in this cool video, there's lots of cool videos on the internet of people dropping things. It's really cool. Anyway, this guy is dropping looks like a champagne bottle off this building top. Okay? As soon as he lets go of the bottle, okay, it's in what we call free fall. And what free fall means is that an object is falling only under the influence of gravity. Now, when I say falling, that's a very loose term because an object can be falling upwards. When you throw something upwards, that object is still accelerating downwards, and that acceleration downwards seeks to slow down the object, which is why it stops at the top of its path and then goes downwards. Okay, so again, falling upwards is possible. Okay, so in this case with the champagne bottle, just want to talk about the forces acting here. Okay, we have a force of gravity equals weight equals m times g, which is acting downwards, and then g is acting downwards at 9.8 meters per second squared. Okay. Now, there's also an upward force acting on the bottle, which I'm going to talk about in just a little bit, and that's called air resistance. Okay. And any object moving through a fluid experiences some sort of resistance, which is in the opposite direction to the direction in which it's moving. Talk about that in just a minute. Note also the double arrowhead on the acceleration vector, which you see a lot. Okay, all right, so those are the forces acting on it. Okay, all right, so free fall, it turns out free fall is uniformly accelerated motion in a straight line. Okay, which is good for us because that's what we study in this class. We generally don't, with the exception of circular motion, we don't really deal with acceleration in anything but a straight line. So acceleration for us, it's sufficient to quantify it as being either positive or negative. We'll talk about that more later. Okay. Now, a feather and a stone, they don't fall at the same rate unless they're in an evacuated tube with no air. Now, why would that be? Okay. Maybe you've seen this video. I can't remember if I showed it to you last year. This is astronaut David Scott on the Apollo 15 mission in 1971. He's on the moon where there's no atmosphere, there's no air resistance, and he's dropping a feather and a hammer, and you can see that they hit the ground at the same time. Okay? When air is present, what happens is the following. Okay? Air rubs against the object and creates a frictional force which opposes the direction of the motion. The effect is to slow the object down. Turns out that the faster the object falls, the more air rushes up past it, and therefore the greater the air resistance acting upwards, countering the force of gravity, which is the weight acting downwards. Okay. Now, turns out that when the upwards force of frictional force of air resistance equals the downward force of the weight, the object is no longer speeding up, and it's called terminal velocity. Okay, so we're going to define this term fluid resistance being any force acting opposite to the motion of an object traveling through a fluid. Sometimes we call it drag or air resistance through the atmosphere, but it occurs in any fluid. It occurs in water, cooking oil, motor oil, any sort of gas. Gas acts like a fluid. So it's important that you understand this concept of air resistance. Okay, all right. Okay, so again, with air resistance, with a fluid present, the effect is to slow the object down. What that means is that you have a negative acceleration, okay, and a negative F, since F equals ma, okay? And when I say negative, I mean negative being the opposite direction to the motion of the object, okay? All right, so when this negative force, upward acting in the case of something falling, is the same as the weight, the object will no longer accelerate, okay? So I have F sub d being the drag force here, and m sub g, notice how the lengths of these vectors are the same, okay? All right, so F sub d equals negative w as vectors. Okay, if we talk about the magnitude of these, we can just simply say that the drag force, the magnitude of the drag force equals the magnitude of the weight. If that's the case, there is no force acting on the object, in this case the skydiver, and then the net acceleration, the acceleration of the skydiver is 0. This sigma here means sum. So the sum of all forces on the skydiver equals 0 newtons. And the sum of all forces is equal to m times the sum of all accelerations. So if that's 0, then the acceleration is actually 0. Okay. So here's a little GIF over here showing an object falling that's achieved its terminal velocity. That's pretty cool. Okay. If you have an interest in the way that airplanes work, or foils on aircraft or aircraft wings or aeronautical engineering, this is pretty interesting. A lot of times you see diagrams that shows the flow of air, the flow of fluid around an object falling through it. Okay, so this one right here would be something like wings. You can see that the greater the cross-sectional area that is in the direction or perpendicular to the velocity of the object, the greater the air resistance. So you can see things that are like, this is why an airplane wing is shaped like it is. In that case, you don't want a lot of air resistance, okay? A ball has all this crazy motion behind it as it goes through a fluid, okay? Pretty cool stuff, all right? Now, the formal definition of terminal velocity is as follows. The velocity of an object when the sum of the fluid resistive force and the force of gravity is 0. We've already gone through that. Those are the conditions I've talked about on this slide. Since the net force on the object is 0, the object no longer accelerates, so therefore the change in velocity is 0, which of course the change in velocity equals acceleration times time. So therefore acceleration is 0 because time can never be 0 because things always take place in a finite amount of time. Okay? All right, remember with air present, the faster an object falls, the greater the resistive force of friction. Okay, for small speeds, it turns out that the resistive force is proportional to the velocity of the object. Okay, for larger speeds, and remember these conditions hold for any fluid, it turns out that F is proportional to v squared. All right. Now, in this case, for the skydiver, back to the skydiver, remember that F sub d equals mg. Okay. When I say small speeds, I'm talking about the speed of a skydiver would be something more or less a small speed. Okay, so F sub d equals k v sub t equals mg. Okay, if you solve this for v sub t, you get that mg over k equals the terminal velocity, where k is a constant that depends on the nature of the fluid and the object moving through it. Okay, all right. So we'll do this in class. Objects falling through a fluid. Looks like this is like a steel ball falling through cooking oil or something. Super cool. Look at the the patterns made by the air that's stuck behind it. Super cool stuff. We'll look at all this stuff in class, okay? You need to be aware as IB students of what the VT graph will look like for an object falling through something where air resistance is not negligible, okay? So here's a situation right here. This could be a ball falling through air or falling through a fluid or something. Notice it starts off going very well, it starts off at rest, okay? And then it speeds up very, very quickly, okay? Or sorry, slows down very, very quickly, and then it kind of evens off up here. The terminal velocity of this object depicted in this graph, it looks to me to be about 50 meters per second. The corresponding acceleration against time graph would look something like this, okay? So it's slowing down, right? Initially, it's going about 10 meters per second squared, so this could be, this is probably a graph of something being dropped through air. All right, so it starts off going 9.8 meters per second squared, and then that acceleration slowly decreases until you get to 0. And again, at around 22 seconds, this object has achieved its terminal velocity of about 50 meters per second. You can see that, okay? And these diagrams over here give you an idea of how the vectors change as an object speeds up, okay? All right. Okay, so we're going to do a couple of examples to round out this video. Go ahead and pause this and then try this problem on your own, please. Okay, so we have a skydiver where I'm giving you the mass of 80 kilograms falling vertically with a constant speed. Okay, what's the upward force acting? Okay, well, clearly if the person is falling at a constant speed, that's the terminal velocity. Okay, and in that case, the weight is actually equal to the upward force acting on the skydiver, so it's 784 newtons, okay? The fact that that they give you 50 meters per second as the terminal velocity is actually not relevant in this problem, okay? Another example, try this one. Okay, so in this particular graph, we're showing the variation in time with a speed v of a ball of mass 0.5 kilograms that's been released from rest above the Earth's surface. Force of air resistance is obviously not negligible. Assume the acceleration of free fall is 9.81 meters per second squared. From the graph, determine the terminal velocity of the ball. Well, that's pretty straightforward. Again, if you follow my reasoning with the previous slide, you can see that it's where the curve becomes flat, where the gradient is 0, which is about 25 meters per second, right up here in this area right here. Okay. In the space to the right, draw and label the arrows to represent the forces on the wall at 2 seconds. Okay. So at 2 seconds, it clearly has not achieved its terminal velocity. Okay. So you have the force of gravity acting downwards and air resistance drag going up. The most important thing here is that the length of this vector is significantly less visually by eye than the length of this vector. And if this were an IB past paper, this is an IB past paper question, they would mark you on whether the top vector is shorter than the bottom vector.